something I've been interested in for a long time is operating systems and how they work and what they do and the relation between how my job as a programmer relates to the job of the operating system and the interfaces that they provide us and all that kind of lovely stuff. And in order to get a good idea of how they work, it's difficult to start at something like the Linux kernel because it's huge, complicated, and it's a starting point that is very much the deep end, and it's hard to make progress. But fortunately, the awesome people at MIT have come up with something they call the xv6 operating system, and the idea behind it is it's a re-implementation of Unix v6, which was the operating system written by Koenig and Ritchie to run on the PDP-11 back when they were working at Bell Labs. But the code for that is quite old, and it was designed to run on a machine that isn't really used anymore, so they've got this more modern implementation. And it's written in C, as one would expect with an operating system. I tried to clone the repo from the place that they recommend you do, but I had problems with that. Fortunately, they have a mirror on GitHub, which works, and if we go, I've created a virtual machine for this purpose. If we git clone the repo, it all should work out fine. Ta-da! And now we should have xv6 source code on our machine. And it's a full working operating system. We can prove this by building it. Cool. And we'll see that we have a thing called kernel. And it would be very, very slow if I try to install this on a physical machine and restart into it every time. So the project uses a piece of software called QEMU, which is an emulator that can run all kinds of different systems and different architectures and so on and so forth. And they also offer an option. So if we just boot straight into it with QEMU, we get this additional window, and we drop into a shell where we can run commands. And you can see on the right hand side as well, we can also run the commands. So we have this graphical window which is showing console emulation inside of a full emulator, and we also have console emulation on one of our own consoles. So to get around having two windows at the same time, you can ask QEMU to start up in what's called no-X mode, which is no-X server, which is the graphical windowing server for Linux systems. So if I press Control A followed by C, I get to the QEMU terminal, and I can type quit from there to exit out. So let's try and make QEMU no-X. And you can see we don't get the other window this time, we just get dropped into a terminal. That is the operating system represented by the code that the people at MIT have written. So this is inside xv6, which is pretty cool. It compiles, it boots, and it has a console, and it's doing things like running additional processes. So we can cat the readme. You see it's quite slow. I'm not 100% sure why. It's something we could possibly figure out. So yeah, it boots, it runs. Something I'd like to go through a series of videos that analyze the different aspects of it, from how it boots up to how it schedules processes to the tools that you can use to introspect operating systems. For example, there's an additional make target called make no-X GDB. GDB stands for the GNU debugger, and it's an amazing piece of software that you can use to stop running processes and step through them and inspect variables and all that awesome stuff. You can see if we get only so far this time, and it's because we are listening to a port and waiting for GDB to connect. So I'll open up a separate terminal and I'll cd to the right directory, open GDB. We get some warnings because it's trying to auto-load configuration files, and the xv6 project provides you with files that will auto-connect to your machine running, your emulator running xv6, but it doesn't do it by default for security reasons, which is fine. What we'll do instead is we'll say target mode 26,000, which is the port that it was listening on, if we see that. So if I run this, so we're now remote debugging on that port, but it doesn't have a symbol table, so it can't tell us where we are. And to get around that, we just say file kernel. Program's already being debugged. You should want to change the file, yeah, sure. So it reads the symbols, and now we have a rough idea of where we are. We can't run disassembly just yet because the kernel hasn't actually started. So in order to actually begin, we type run. Oh, whoops. We type continue, my bad. And we can see on the right hand side our kernel continues booting, and we can list stuff. And if we want to inspect what's happening at a given point, we can type Control-C in GDB, and it will stop this. So you'll see I can't type here anymore. And you can see we are in some part of code that acquires a lock of some description. We can disassemble, and we can see we're at a certain point in the assembly. If you have a, so there are two different types of writing and viewing assembly language. There's the Intel type and the AT&T type. I believe those are the names, or the GNU type and the Intel type. And I prefer, and this might be controversial, what was the command? So I'm a fan of the Intel syntax. So I could set disassembly flavor to Intel, and next time when I write disassembly, you can see it is a different type of assembler syntax. And this is a personal preference, and I'll probably be using this throughout the series of videos. I find it easier to read than the other syntax. But from here we can, I believe we could step, and we just get to successive lines of code. And this will be super useful later on when we're going through routines and we want to see, for example, we can do in for locals and the result of wherever we are currently. So if I list the current instruction pointer, it should show us roughly where we are. We're in this function, and we can see that we're issuing volatile raw assembly, which we'll go into far more detail on what this kind of stuff means in later videos. This is an introduction to what the xv6 kernel actually is, how it looks, showing that you can clone it, compile it, run it, and if operating systems are something you find interesting, then I would hope that walking through this code base and trying to understand every part of it is a project you'll find super interesting and helpful.